What would the point estimate for the true mean be? 11.19, yes. The point estimate for the true mean. We know what the claimed mean is, but we don't know what the true mean is. So we're going to use the sample mean, x bar, of 11.19 as the point estimate. What's the population? All Oreos. So what's the sample? 30 Oreos. What's our statistic? Yep, x bar equals 11.19. What would the parameter be? The true average or true mean weight for all Oreos. What symbol should we use to represent this parameter? Mu. So we use x bar if it's a sample, and we use mu if it's the true population average. So there's something that I noticed as I was grading the test the other day, and I want to make sure to point it out right now since we are talking about parameters. When you're doing the parameters, either in confidence intervals or in tests, don't just write the word parameter and then define it. You have to say what that parameter is. Is that parameter P? Is that parameter P1 minus P2? Is that parameter mu? That's going to be really important. They're going to be looking for that. So you definitely want to define what it is, but you also want to have the correct symbol to go with it, because you'll be using that idea elsewhere in your confidence intervals or elsewhere in your significance tests. And so here you are defining what that symbol means. All right. Was the sample a random sample? Yes. Why is that important? Yep, allows us to generalize the population. You guys are getting really good at that one. Okay, so that would be our random condition, just like normal. What is the formula? You can go to the formula sheet for this. What is the formula for calculating the standard deviation of the sampling distribution of x bar? Yes. We have sigma, which is the population standard deviation, over the square root of n. What condition must be met in order to use that formula? 10% condition has to be met. Did we meet it? How do you prove it? Yes, 30 is less than or equal to 10% of all Oreo cookies. So that's our 10% condition. Or what are we actually checking there? Rather than calling it 10%, what are you checking for? Sampling without replacement is okay. We're checking for independence there. So it's fine if you label it 10% condition when you are checking it on your page, but just tuck into the back of your mind, what we're checking for there is that sampling without replacement is okay, so that we have independence here. In the formula for standard deviation of the sampling distribution of x bar, we don't know sigma. If we did, if we knew what sigma was, then we would know what mu is. But we don't know what mu is. So instead, we're going to use S. What was S? 0.08. So we call this the standard error of x bar. This isn't the standard deviation, this is the standard error. It's basically the same thing. We just can't call it standard deviation because it doesn't apply to the whole population, it just applies to our sample. So we're going to do S over the square root of n, so 0.08 over the square root of 30. What did you get for your standard error? 0.0146, yes. All right, one more question on this page. Would it be appropriate to use a normal distribution to model the sampling distribution of x bar? Let's just start with yes or no. Do you think it would be appropriate to use a normal distribution? Yes. Now let's talk about why. What do we call this condition when we're doing proportions? Large counts. But large counts has to do with successes and failures, right? We do n times p. We don't have a p, so I can't do large counts here. What can I do? Central limit theorem. And what does the central limit theorem say? If n is greater than or equal to 30, then we can assume normality. So we call this our normal or large sample condition. So for proportion, we have large counts. For means, we have large sample, but we're still checking for normality there. There is one other freebie that we can sometimes get. They didn't give it to us on this problem, but the other way that we could show normality is if it says in the text, the population distribution is approximately normal. If we know that the population distribution is approximately normal, then we get to assume normality for the sampling distribution as well. So that would work even if we didn't have 30, but it either has to be the population distribution is approximately normal, or we have at least 30 in our sample. So far, so good? All right, let's flip this page over. When finding the margin of error for a confidence interval for a proportion, we use Z star. Do you guys remember using Z star? That was our critical value, and we could look it up using inverse norm, right? For a mean, we use T star as the critical value. To find T star, we're going to look that up in the formula sheet packet. I'll show you guys where that is, but you go ahead and pull out that formula sheet. So why do we need to use T star instead of Z star? The reason that we need to use T star instead of Z star, this would be how you would calculate Z. Statistic minus parameter divided by standard deviation, right? Do we know mu? Do we know for sure what mu is? No. We're having to estimate that. Do we know sigma? Also no, we're having to estimate that. In fact, instead of sigma, we have to use S, the sample standard deviation. Because there are two values that we don't know that we're having to estimate, we have to use what is called a t-distribution, because my normal distribution would look something like this. My sample average would be on here, normal with mean mu and standard deviation sigma divided by square root of n. Because we have introduced some estimations, we have more variability. What does variability do to my graph? If I have more variability, it gets wider, right? So a normal curve looks like this, the black one. A t-distribution has the same symmetric shape, but it is wider. It's a little shorter and it's a little wider than a standard normal curve. Exactly how wide it is and how short it gets depends on what we call degrees of freedom. The higher my degrees of freedom, the closer and closer this t-distribution gets to the normal curve. In your formula packet, I want you guys to locate table B. Does anybody need to borrow a formula sheet? Please don't write on them. I have to print some more ones somewhere out anyway. Here we go. You're welcome. There you go. There you are. Anybody else need to borrow a formula packet? There you are. You're welcome. So table B is on the last piece of paper in the packet. It's the third sheet of paper, and it's on the front side. Notice it looks a lot like a normal curve there. Let me see if I can actually get one up on the screen. So that'll make this easier. Okay, that should fix that. All right. So formula page, we're going to go to page 3. And I want you to look carefully at this distribution. What do you notice right down here? It says T star. If you flip back a page, this was our Z table. The standard normal curve is Z. We are working with a T distribution. So right here. Down the left-hand column, we see DF. This stands for degrees of freedom. And across the top, we have the tail probability. Do you guys remember when we did 95% confidence intervals? Does anybody happen to remember what the Z star was for a 95% confidence interval? 1.96. It was almost 2, right? 1.96. Which tail do we have, left or right? We have the right-hand table. Is that the same thing as we had in a Z table? Z table, we had the left tail. With a T tail, with a T distribution, they give us the right tail. So let's look at what our critical value would be for a 95% confidence interval. I'm going to come all the way down here. Look down here, confidence level C. Do you guys see this across the bottom? That corresponds to across the top. Across the top is alpha levels for significance tests. Across the bottom is confidence levels. Look at the very bottom row. What does it say the degrees of freedom are? Infinity. So absolutely enormous, right? Look at 95% confidence interval. What is the critical value? 1.96. The higher our degrees of freedom, the closer it gets to a Z, until if we have infinite, it is the same as Z star. All right, let's hop back. And the degrees of freedom, which we will calculate by doing n minus 1. What was our n? 30. So n minus 1 would be 29. So we're going to go over to table B. If it'll go over for me. We're going to do a 95% confidence interval, so I'm looking here. And I want 29 degrees of freedom. What is our T star for 29 degrees of freedom with a 95% confidence level? Yes. 2.045. Right here. 95%, 29 degrees of freedom. So this is our T star, our critical value. All right. So now that we know what our critical value is, I want you guys to calculate the margin of error, find that 95% confidence interval, and interpret the intervals. So 10, 11, and 12. I'm going to give you guys a couple of minutes to work on that in the groups that you were working in before. Look back at the blue packet for how we did this with proportions. But I'm going to give us, let's see, that's 3 questions. Why don't we take 5 minutes and see if that gets us through those 3 questions. So 5 minutes to calculate the margin of error, the 95% confidence interval, and to interpret the 95% confidence interval. So we use T star instead of Z star. So when you're looking back at the blue packet, anywhere we use Z star, you're going to use the T star value instead. And this is a dark blue packet for chapter 9. Or sorry, chapter 8. Sorry, chapter 8.
I don't think I needed to do the X bar. The margin there. Gives your budget. Oh, yeah, I guess I don't need it right now. Well, I'm gonna do that.
Standard error. Because standard error for proportions, we have a different result. So that one, we actually did all the calculated.
What's your bottom?
I just did it right.
Oh, yeah, wait.
I know, but I just did it.
I remember I showed them.
Oh, it's 0.04.
No, we are
Yeah, it would be.
95%. You remember this one? X bar for
X bar instead of P hat. So we already found our standard error. Standard error, we have a 5. That's our standard error.
very specific formula for it.
Remember, we found standard error. We did that on the front page. Standard error is what we calculated in number 6 on the front side. So you don't need to recalculate standard error. We already have our standard error.
Yeah. That's fine.
But what if I was minus?
margin of error.
How do we do that?
This is how we do it. Critical value, D star. D star. And then times the standard error. Standard error we did on the front.
I just say use T.
So if you just times those two together, that'll give you the margin of error. And then to do your confidence interval, then you'll do the 20 plus minus whatever you get from the top.
That's what I do.
You're welcome.
When we calculate we're just using the
So this is for-
0.015,
This is for two sample.
and then for one
So-
it's just
Here, let's flip back a couple pages. Backwards. Let's see. One more. Yep, I think if you flip it over, here we go. There's the general formula. And so our specific formula, the point estimate when we did proportions was p hat. But here it's going to be what?
standard error.
Not instead of p hat. What's the point estimate? We wrote this down on the front side too.
11.19.
11.19, so that's an X bar. And then T star, and then this is how we calculated the standard error for proportions. But the way we calculate standard error for means is like this. So we did this. So this, but with S up on top, instead of that big square root thing. Because this is how you calculate standard error for proportions, but this is how you calculate standard error for means.
So it would be 11.19 plus 2.045, and then the standard.
Times the standard error, which would be this number right here.
So for the, are we putting the point 15 or the 0.08?
The 0.015 or 0.01546 or whatever it was. So the margin of error, you just need to do this part, which you'll need to change that numerator so that you don't get confused. Because remember, we're not calculating it like this. So I would recopy what you have from the front side, which is S over square root of n.
And that's for margin.
We do T star times S over radical n. Does anybody have a margin of error that they feel confident in sharing? Yes. You said 1.015? I got something a little smaller. Again, I'm just looking for the margin of error. 0.03 if you round it out to 2 decimal places. Let's look at how we get there. So from the margin of error, we do T star times the standard error of X bar. So 2.045 times 0.0146. and I got 0.0299 or 0.03. I'm fine if you round it either way. Thank you. You're welcome. All right. So that's our margin of error. So again, here's my T star, and the standard error is this, which was this, calculated on the front side. Yes? 0.0298, that'd be fine. That'd be perfectly fine. I would even be fine with 0.03. 0.03 would be fine. All right, so now calculating the confidence interval. For the confidence interval, it's point estimate plus or minus the margin of error. What was the point estimate from the other side? 11.19 plus or minus our margin of error, 0.0299 or 0.03. And so then we do our confidence interval. You have to subtract first because we always need the smaller number in the interval first and then the larger number second. It should be just like you would read it off of a number line. So for those of you that use 0.03, what is 11.19 minus 0.03? $11.16. And then what would 11.19 plus 0.03 be? 11 point what? 11.22. So I did my margin of error with a little bit more decimals, but notice I got very, very close to the same thing that was said if you use 0.03. I got 11.1601 to 11.2199. So now interpreting that interval. How would you start the interpretation for a 95% confidence interval? We are 95% confident that the interval from 11.16 to 11.22, what kind of units should we put with that? With proportions, that's just percentages, so we don't put units with that. But what are we talking about here? The average what? The average weight measured in grams. So from 11.16 to 11.22 grams captures what? Yes, the true mean weight for all Oreo cookies. You can use the word average or you can use the word mean, but I would not use both words because it's just redundant. You're saying the same thing twice. So average or mean. The true mean weight, the true average weight of all Oreo cookies. All right. Let's see if we can write a specific formula based on what we did here. This 11.19 was the point estimate, but what did we call this on the front page? We called that X bar. So X bar plus or minus T star times, how did we calculate this? S over square root of n, yes. So our specific formula here would be X bar plus or minus T star times S over the square root of n. Here's the point estimate plus or minus T star times standard error of x bar. According to Nabisco, the average weight of an Oreo cookie is 11.33 grams. Does our confidence interval provide convincing evidence that the true average weight is less than 11.33 grams? Yes, why? Yeah, 11.33 is not in the interval. All of the numbers in the interval are smaller than 11.33. All of the plausible values, all of the values contained in the interval are less than 11.33 grams. We've covered all of the differences now between doing this with proportions and doing this with means. The standard error is calculated differently. We no longer do radical and then p times 1 minus p over n, or p hat times 1 minus p hat over n. We don't have to do that because that's how we did standard deviation or standard error for proportions. For means, it's much simpler, s over square root of n. We still have our conditions that we have to check, random 10%, and then instead of large counts, we do what? Central limit theorem, or large sample. If we are told that the population distribution is approximately normal, then we get our large sample, or we get our normality. If n is greater than 30, then we can use central limit theorem. Sometimes we will have a situation where we don't know what the population distribution is, and we also won't have at least 30 in our sample. If that's the case, then we're going to look at our sample data, and we're going to plot it, like with a bar chart or with a dot plot. As long as it shows no strong skew or outliers, we can go ahead and assume normality. But you have to inspect a graph in that case. So population is approximately normal, or we have at least 30 in our sample, and so we use central limit theorem. Or when I plot the sample data, it doesn't show any strong skews or outliers. We've got 3 different ways that we can get here. Critical values, we use Z star for proportions and T star for means with degrees of freedom n minus 1. We'll look at table B to find our T star. I want you guys to look down the left-hand column on that table. I'm going to pull it up on the screen. What do you notice happens after we get to 30 degrees of freedom? It goes up by 10s, 40, 50, 60, and then it goes up by 20s, 80, 100, and then it jumps all the way to 1,000. And then from 1,000, it goes on to infinity. So it does not have every degree of freedom that we might see. If we are looking at a situation where our degrees of freedom does not match one of the degrees of freedom here on table B, we're going to round it down to the next closest. So if it was 79, I'm not going to round it down to 80. I wouldn't round it to 80, even though 79 and 80 are close together. I would round it down to 60. So always round down, no matter how close you are to that next one. If you haven't actually reached it yet, you're going to round down. Always round down. All right. Let's take 5 minutes for you guys to do the check your understanding. You can do it alone or with your partner. And then we will compare in 5 minutes. I took these away from you guys too soon. Oh, so sorry. I forgot. You're welcome. Alex.
Okay, so margin of error. How do we find it in?
So that's not your margin of error, that's your T-star. And all I need you to do is find the T-star here. You're using table V to find T-star. That's all I want you to do. So instead of ME, just write T-star and it's good. Or I guess you have it back here. Yep. Now you can go on to part B. For number 1, parts A and B, all you're doing is figuring out what's the T-star that you're using. You don't have to calculate the margin of error there. You're just finding T-star. Yes.
So, for this one, we were gonna say the conditions haven't been met, but if n is greater than or equal to 30, would that mean that it has been met even though it's skewed?
Well, how many conditions do we have?
3.
We have 3 conditions. We got to check all 3. But when you were talking about n being greater than or equal to 30, that would meet the large sample condition.
Okay,
even though it's
okay.
skewed, yes.
Okay.
So the only time we care about the skew is if we have less than 30.
Okay.
If we have less than 30, then it being skewed is going to be a problem. But if we have more than 30, the sampling distribution, even though the population is skewed, the sampling distribution would still be approximately normal.
Okay.
You're welcome. Not necessarily to the nearest number, but when I say round down, like let's say I had a sample that had 80 in it. Degrees of freedom would be 79 then, right? And minus 1. When I look down here, 80 is on there, but my degrees of freedom is 79. I would have to round it down to 60. So always go down. You're not necessarily going to the closest number. You're going to whatever is behind what you just found.
Okay.
If it's not exactly on there.
Sorry.
Wait, 10% condition. Will we just take all adults or we
All
use
adults.
that number?
No, yeah, I would not use that number down there. You can see it better on yours than I can on mine even. Look how fuzzy it is on mine. What would the T-star be for part A? Yes. Degrees of freedom would be 25, which is one of the degrees of freedom that's on there. 2.485. 99% confidence interval from an SRS of 85 observations. How many degrees of freedom would we have? What would the degrees of freedom be? 84. Is 84 on the table? So we are going to round down to 80. Use degrees of freedom 80 because, again, if necessary, we round degrees of freedom down for table B. What did you guys get for the T-star here? 2.639. Nicely done. All right, let's talk conditions now. What are the three conditions? Random, 10% of normality. Do we get random? Quote it to me. Where do we get it? Random sample of 1640 adults. You do need to quote that whole thing. Don't just quote random sample and put a check. Random sample of 1640 adults. Why do we care about that? So we can generalize to the population. All right, then you said we have 10%. So I need 1,640 is less than or equal to 10% of all adults. Why do we care about that? Independence. Sampling without replacement is okay, so we get our independence. Last condition is normality. When you look at that graph, is it skewed or does it have outliers? Is that a problem here? No, because why? Central limit theorem, our sample is at least 30. The only time we care about the graph is if we don't have at least 30. So always check, is your population normally distributed? If so, you're good here. If that doesn't work, do you have at least 30? If that doesn't work, then you go and look at the graph. And this is so the sampling distribution of X bar is approximately normal. For tomorrow, we are going to be using some data that you guys will provide. What I need you to do tonight, other than maybe get started on your homework, I need you guys to figure out on your phone, where do you go to see your usage day by day? So I know how to find it on an iPhone. I don't know how to find it on the different Androids. Figure out where to go on your phone, where it will tell you how much, like how many minutes you were on your phone for each day. We're going to sample one day tomorrow, but I need you to be able to go in and find that data. Homework is due on Friday. Homework is due on Friday.